welcome to the next lecture of Digital Control in Switch Mode Power Converters and FPGA based prototyping course. Before we move forward, let's have a quick recap of the last lecture. In the last lecture, we started the discussion with STM32 microcontrollers, various options available. Then we discussed the difference between analog and digital control. Then in particularly digital control, or we can say it's a digital power, that what all features or peripherals required within the microcontroller to be a best fit for any digital power applications. Then we focused our discussion on STM32G4 microcontroller, which is mainly meant for any digital power applications. Then we discussed about various features and the complete ecosystem built around it. We also discussed the various hardwares and the software tools available for STM32G4. Particularly for the hardware, we mentioned about the Nucleo boards, discovery boards, and several evaluations boards. While for the software, we discussed about the STM32 CubeMX, various IDEs, and digital power workbench. In this lecture, we will be starting with the overview of STM32 Cube and STM32 CubeMX, where STM32 Cube is the name of the complete environment, also an open source from ST Microelectronics, where STM32 CubeMX is one of the tools in it, which generates the C code, and we will be discussing in details in coming slide. Then we will be focusing our discussion on STM32 Nucleo boards, which will be used for testing the code generated from STM32 CubeMX. Then we will be moving step by step, starting with the STM32 Cube installation, and we will be having a hands-on experience and various examples in details where we will be doing the peripherals initializations, code generations, and programming the microcontroller on the Nucleo board. Let's start with the STM32 Cube overview. STM32 Cube brings all the tools and embedded software for STM32 users in a simple and integrated manner. STM32 Open Development Environment, or we can call it as STM32 ODE, it allows developers to verify their design assumptions and move quickly from ideas to a proof of concept. Moreover, STM32 ODE offers a comprehensive entry point to choose the hardware, firmware, and software from the functions required by the applications. To complete the picture, ST Microelectronics offers a business-friendly solution. Like there are no license terms and conditions, developer can be benefited from the free and open source software. Also, the embedded software and the software tools from ST are available at no cost to developers and can be openly shared provided they are using STM32 devices. On top of that, quality remains a top priority. Hence, the core components are tested by ST before their release, and ST is committed to follow good practices guidelines like MISRA, code checkers, validation reports, etc. So in a nutshell, STM32 is a comprehensive time-saving solution for STM32 users. STM32 includes a set of user-friendly software tools to cover project development from conception to realizations. These tools includes the first one is the STM32 CubeMX. It's a configuration tool for any STM32 device. This easy to use graphical user interface where the user can initialize the peripherals and the tool generates the initialization C code. Particularly for this tool, we will be having a dedicated slides and we will be having several hands-on sessions with several examples. The second one is the STM32 Cube IDE. It's an integrated development environment based on the open source solutions like Eclipse. This IDE includes compilation, reporting features, and advanced debugging features. It is similar to IR, Kyle, and other available IDEs. The most important is it's an open source. The third one is the STM32 Cube Programmer. It's a programming tool which provides an easy to use and efficient environment for reading, writing, and verifying devices or external memories via a wide variety of available communication media. It can be JTAG, SWD, UART, USB, I2C, SPI, etc. The fourth one is the STM32 Cube Monitor. It includes powerful monitoring tools that helps developer fine-tune the behavior and performance of their application in the real time. Apart from these software development tools, STM32 Cube also offers certain packages. The first one is the STM32 Cube MCU and MPU packages, where we all know MCU is the microcontroller and MPU stands for the microprocessor. So this package offers all the required embedded software bricks required to operate the available set of STM32 peripherals. They include drivers, middleware, and a lot of example code used in a wide variety of real-world use cases. The driver includes the hardware abstraction layer, lower level APIs, and the middleware components. The hardware abstraction layer, or we can call it as a hall layer, it enables the portability between different STM32 devices via standardized API calls. While the lower level APIs, it's a lightweight, optimized, expert-oriented set of APIs designed for both performance and runtime efficiency. But I would suggest that for most of the applications, Hall, or we can say hardware abstraction layer, will fulfill our requirements. But for the digital power applications, we can start with the hardware abstraction layer. Eventually, we have to move towards the lower level APIs, because in digital power applications, for all the protections and the control algorithm, we have to take the decision very fast. And the middleware, it includes the RTOS, USB library, file system, TCP IP stack, touch sensing library, or graphical library depending on the STM32 series we are using. It also includes the RF stacks such as Bluetooth, OpenThread, Zigbee, LoRa, Sigfox, again depending on the specific STM32 wireless series we are using. On top of it, there is also an STM32 Cube expansion packages. These packages are application oriented. Mainly they are complementing and expanding the STM32 Cube MCU package with an additional embedded software bricks. The STM32 Cube expansion packages come either from ST or approved partners to create an extensive and scalable embedded software offer around the STM32. STM32CubeMX, like we have discussed, it is one of the software tools of STM32Cube Open Development Environment and is of prime importance to us. It's a graphical user interface tool that guides the initial configuration of the firmware projects. Very soon we will be seeing that how exactly it helps for selecting the right microcontroller for our applications, how we can configure the pinout configurations, the clock, peripherals, and different modes. So this is the screenshot of the pin configuration that is being done. The most important thing, the initialization code, it generates the C code and it generates the project for three different IDs. The first one is the IR, the second is the Kyle, and the third one is the STM32Cube ID. STM32Cube ID is then open source. STM32 Nucleo development boards. These Nucleo boards we have discussed in the last lecture, but it is worth mentioning here, as soon we will be starting with the actual working of STM32CubeMX tool, and we all know this tool helps in generating the C code and the entire firmware project. So this firmware need to be run on some hardware in order to visualize the outcome if the firmware that has been written is right or not as per expectation. In order to demonstrate, we will be using these Nucleo boards, though there are large number of Nucleo boards, but we are targeting digital power applications, so we will be using STM32G4 microcontroller based Nucleo board, which you can see in my hand. Just a quick glimpse about this Nucleo boards. These Nucleo boards allow developers to try out new ideas and quickly create prototypes. Thanks to various connectors present on these boards, which can extend their capabilities using multiple application related hardware add-ons. When I say the hardware add-ons, it can be Arduino Shields and the X Nucleo boards. There are three types of Nucleo boards: Nucleo 64, Nucleo 144, Nucleo 32 ports. So this number depends on the pin count of the microcontroller. This Nucleo boards also integrates ST-Link debugger or the programmer, so there is no dedicated hardware required to program the microcontroller. Let's start with the STM32CubeMX. Firstly, we will be starting with the downloading and the installation process. Then we will be moving to the hands-on or the live experience. In order to download the latest version of STM32CubeMX tool, we can go to ST website, that is www.st.com.
We can directly go to the tools and software sections, or we can go to the search bar menu options and search for STM32 CubeMX tool. It will be showing a couple of options. Here we can select STM32 CubeMX initialization code generator. Now it will take us to the main page of the tool. Here we see an option of getting the software and downloading the data brief. Below there is also an option of the documentation where we can see various application notes, user manuals, release notes and the presentation. Now I click on get software. It will be showing me three options of the Linux, Mac or the Windows machine. So as I'm having the Windows machine, so I'm clicking on the get latest version for the Windows. License agreement we can accept. Now it will be taking to a login or the register page. As I'm already having a login, so I'm clicking on the login. Otherwise we can fill the details and register with a suitable email ID. Here, after doing the login or once you have registered, we can get the software download and install on our PC.
Some important points while installing the STM32 CubeMX tool, that it requires Java RE to be installed in our machine. Just in case you don't have it on your PC, you can download it from the given link and get it installed. And in the updated settings, there are two options: update settings and the connection parameters. By default, there is nothing required to be changed here. Just in case you are using a workplace PC or work machine and you require to set some proxy, you can do it appropriately over here.
On successfully installation of STM32 CubeMX tool, we can launch the tool, and this is the home screen of the tool in which we are able to see various options. On the left side, we can see the various recent projects we have been working on. It is showing the list. The other option is the new project. If we want to start the new project, in that also there are three options. If we have any pre-selected MCU in our mind, or if we want to select the MCU for our application, we can use this, and depending on the peripherals required, we can select the best MCU in terms of the cost or the power or the size or the package, whatever is our requirement, and accordingly we can initialize the peripherals, and accordingly we can generate the C code. We will be working on this section a bit later. The other option is the start my project from ST board. When we say the ST board, it can be the Nucleo boards or the discovery boards. When we use this option, so the file that we'll be working on, all the peripherals will be initialized as per the hardware. If you want to modify that also, that option is also available. So the third option is start my project from examples. As I've been telling you that there are several examples that has been predefined for several Nucleo boards, several discovery boards. We can use those particular examples and evaluate. On the right hand side, we can see another options, check for updates. If we click on check for updates, it will be telling that what all softwares or the packages we have installed, and is this the latest version, or there is some another version that we need to update. It will be telling that. So the CubeMX is the latest version that have been installed, but the MCU package, so for the G4 package, it is telling that there is another updated version that is available, and I have the version installed, it's 1.50, while the available version is 1.5.1. So if we want to install, we can just click on install and it will be correspondingly installed on your PC. The other option is install or remove embedded software packages. Depending on the microcontroller that we are working on, we can accordingly select the package. Let's say we want to work on the STM32 G4. So as just mentioned that 1.50 is already installed, but if you want to install the latest, we can just right click here and press install. It will be correspondingly installed on your PC. Just remember the path where exactly all these files are getting stored.
One thing important to mention here, like in our case, we are using STM32 G4 Nucleo board. So I have installed
the G4 package here. Like if you can see here, I have installed this, but in case you don't have STM32 G4 Nucleo board, if you have any other board, let's say F4, so you can correspondingly install the latest version STM32 Cube package. Now we will be started working on this Nucleo board based on STM32 G4 microcontroller. This is the 64-pin microcontroller. These are the various connectors. On the top side, this is the ST-Link, basically the debugger. Also, there are two push buttons. One is for the reset, the power reset, and the another is basically the user push button. We can use it for various purposes. Also, there are few LEDs for the indication. For more details on the Nucleo board, we can always go to ST website, that is www.st.com, and check for the relevant schematics and other documentation, where we can find all the jumper, all the signals, and the connected details. Now we will be moving on to an example. Here we have selected a very basic example of GPIO toggle. The LED is connected to one of the GPIOs and we will be toggling it. This example we will be covering in three ways. With each way we are moving ahead, we will be getting more deeper insight of STM32CubeMX and we will be getting more aware of it. In the first way, we will be directly using the example as provided by the STM32Cube package. In the second way, we will be selecting this Nucleo board. Correspondingly, all the peripherals that are being done in the hardware will be initialized and we will be only working on the application layer. While in the third way, we will be selecting the MCU, we will be initializing the peripherals ourselves, and correspondingly we will be working on the application layer and make our example up and running. We will be using IAR as a IDE, basically integrated development environment. Let's start with the very first way. Let us move to the repository where exactly the package has been installed. By default, it will be installed in your C drive where there is a user and you can find a folder STM32 Cube, and correspondingly repository you can find all the packages that you have installed. So as we are using G4 1.5 version, we can go inside and in that we can see various folders of the middleware, driver, documentation. Now we have to move to the projects. In the projects also there are several Nucleo boards. In our case we are using Nucleo G474RE board. In this board there are several examples of lower layer, mix, templates. This templates is basically for the if we are making some new project on our own, so we can use these templates. So right now we can go to an example and we can go to an example of GPIO and GPIO IO toggle. Now as I just mentioned that we will be using then IAR, so we can go to EVAM. Otherwise correspondingly we can go for the STM Cube IDE or Kyle IDE. So for the IAR we need to go to EVAM. So let me copy this path and open this in a IAR workbench. So this project has been opened here. So we can see in the documentation there is a readme file also where we can find all the details. In the application and in the user there is a main.c file, interrupt.c file, and the whole MSP file. If we go, so the main.c file is already open. If we go from the top, the main function has been started, whole initialization layer, then the system clock. As we have just mentioned that this is an example of GPIO toggling where one LED will be toggling. So this one GPIO port is configured and correspondingly there will be a delay of 100 millisecond in the while one loop that we are working on. So let me connect this Nucleo board. So if you see, it has been connected and now I will be programming this firmware onto this Nucleo board. You can see this LEDs turn screens, means the communication is happening. Just a couple of seconds more. Now the firmware has been loaded and now I make it run. Now if you could see, this LED starts blinking with the delay of 100 milliseconds. So this is the direct example that we have used. Let me just change the delay to 1 second. So this is the 1000 milliseconds correspond to 1 second. I just reload the program again. It takes a couple of seconds to reprogram. Now if I run the program, now if you could see that the LED is blinking with the delay of 1 second. Now I just stop debugging. So the main idea is that it generates not only the C code but a complete project. We can use directly the project as per our application requirements. There are several drivers, hall drivers, as we have mentioned in the very beginning regarding the hall driver. uh, Whatever various communication that we want to use, either UART, timer, or whatever peripherals we are initializing, it will be correspondingly reflected here. Let's say if we are using I2C or SPI, correspondingly driver files will be flashed here and we can use the direct function calls. Test. So the file is saved as test.iuc. If you want to see, I can see that in the firmware nptel there is a folder called test, and in that the file name with the test.iuc has been saved. And now if I click on generate the code, so it is asking that if the latest firmware is package is not being used, so if you want to download it right now or no. So I select no. So here we can choose that if you want to use the latest version or the earlier version that we have. So in the project manager we can do all these settings. So I will be telling you maybe in the next lecture on this project manager file. So now if I click on the generate code, again it will be taking a couple of seconds and generating the firmware project again of 3 different IDs: IAR, Kyle, and STM32 Cube IDE. So by the meantime, if I also show you the folder, if you can see that there are several test folders being created here. Okay, so it has been done. So close it. So it say if you want to open the project and open folder. So I don't want to open the project right now. I just want to open the folder. Okay, so this is the same folder. Again, I want to go to evam and I copy the path and open in the IAR. One thing that we need to keep in mind that right now all the peripherals that are pre-configured for this Nucleo board has been done here. So there is no test example. So in the application layer, we only have to write by ourselves to make the same example up and running. Again, if you can see, if you remember the initial code of the first way, there also we have the hall init, system clock config, GPIO config, the UART, but if you remember, there were few lines written in the while one with the hold delay and the GPIO toggle, which is not the case here. So we have to write this lines right now. So right now, if I go to the driver and go to the hold driver and go to GPIO.c file, in the GPIO.c file, on the right hand side, if you could see that I could find all the functions that has been written here. So I'm selecting all GPIO toggle function here. So I'm copying this function here and pasting it here. Now I want to go to that which GPIO unit, though I know it's PF5. So I just want to go to LED2 pin. I just want to configure. Okay, so this is the LED2 pin and this is the LED2 GPIO port. So I copy the port first and I paste it here, while the pin I paste it here. Okay, so this has been done. Now another function that I want to have is the hall delay. Just to update you that by default, if we go onto the interrupt.c file, the sysdig handler, basically this intake is of 1 millisecond. So whatever the value I pass here, it will be correspondingly multiplied by 1 millisecond. So if I just again pass maybe 10 milliseconds, so the LED2 should blink very fast. Firstly, I need to basically rebuild my project and basically do the complete cleaning and rebuild the complete project. I request maybe if we can focus on this LED2 pin, it is blinking with 1 second delay. So now my project has been built, and now if I download this firmware into my Nucleo board, so the firmware has been downloaded, and if I make it run, if you could see, the LED is almost just like it's complete glowing because the delay is very less. So maybe if I just increase the delay to 100 millisecond, and now I reprogram the microcontroller and see what exactly is the case. The firmware is already downloaded, and I click on run. So now if you could see that we can easily see the 100 millisecond delay. So this is the second way of generating the code. Now I stop the debugging and we move on to the third part. For the last way, we need to click on access to MCU selector. It will be displaying the complete list of microcontrollers, basically a 32-bit microcontrollers, though ST is having 8-bit microcontrollers also. So this is the complete list, though we can select the dedicated MCU that is mounted onto the Nucleo board, but we can squeeze down the list by using the several options available here. So I can choose first the line, I can choose STM32G474, And in order to squeeze down further, let me choose the package. Oh, it's a 64 pin package, so we can use various options to squeeze down the list. So I'm directly selecting the microcontroller which is mounted onto my Nucleo board, that is STM32 G474RET6. So now by the meantime the file is generated. The file generated will be now completely blank with no peripherals initialized. So we have to customize or do the configuration as per our application requirement. So we wait for a couple of seconds till the blank file of this microcontroller generates. We are almost there and the file is here. So now if you can see that the microcontroller, all pins are basically blank, only the VCC and the ground pins are highlighted by the yellow, and we have to configure every pin as per our own requirement. So now we are targeting an example of the GPIO or basically LED toggle. So now we have to switch on to the schematics. So we can go on to the Nucleo G474RET6 page, and there we can have the documentation, the CAD resources, the schematics in terms of PDF. In the documentation we can have several jumpers and all those things in details. While in the schematic, if you can see this LED2 which is now blinking with 100 millisecond delay is connected to a PF5 pin of the microcontroller. So we need to configure PF5 pin of the microcontroller. So we need to configure as GPIO output. So we need to make it high and low in order to make LED on and off. Also on the left side there are several parameters. Firstly, I want to configure my debugging interface, the serial wire interface. So if you could see, that's as I've selected, these two pins are already configured. And now for the GPIO, so this PF5 pin, so the output level, firstly let me keep it high. Output push pull, yes, I want to push pull. So speed, so I can select the high speed. So as per our requirement we can select it. In the user label, so let me put LED2 underscore 2. So just for our, or basically as per the user requirement, we can put the label here, and correspondingly this label will be updated here. Apart from that, there are ADCs, tags, op-amps comparator that is present in the analog section. Also in the timers we have the several timers. In the connectivity we have SPI, I2C, UART, USB, while there are other options, middlewares and others, that maybe it will be useful for the another project, but as of now we need to focus on the GPIO output. So I will be covering a few of these topics in the next lecture. So now we go on to the clock configuration. So as I mentioned just in the second way, that the Nucleo board is having the external oscillators, external crystals, but as of now I want to use the high speed internal, and the maximum speed that the controller can work is 170 megahertz. So we can use PLL loop and make it faster. So I already know the values, but we can play with it to have whatever frequency we want to make the microcontroller work. We can select that. In the project manager, for sure we can set the names, we can set the location. The main thing that we have already seen that I want to highlight here also. So we can use the latest version. If this option is ticked, it is bound to give an error that the latest library is not downloaded. But if we uncheck this and we can select the earlier version that is installed on our PC, we can select that. So right now we can give the name as test1 for this, and again I go to the pin configuration here and save the project. So now if you could see, sorry, in the firmware nptel, this test1 folder is created, and now if I generate the code, so correspondingly you will be seeing that various files are being generated in the test1 folder. Just bear with a couple of seconds till. Okay, so it's done. So I open the folder. Instead of directly opening the project, we can open the project, but I would go to the open folder in order to show you the various files. We can go to the EBAM, again copy the path, and we can open it in the IAR. So this is the project that we have created, in which we have not only used the pre-initialized peripherals, we have configured that by themselves, and right now we have to do the application layer also, like we have done in the second way. So again I go to the main.c file, where I could see that the hall libraries are initialized, system clock, and GPIO unit is there, while again in the while one I have to write my own application layer. So again I go to the drivers, hall drivers, where I go on to the GPIO.c, and the functions here I want to use the toggle pin example. So I copied it and pasted here. Again I can go to the header.c file, maybe not here. So I go to the GPIO init.c. So basically it's GPIO pin 5 and GPIO A. So right now there are no hash defines, which I am searching for it main.h file. And it is GPIO A. And another function that we want to use is hall. Let me just compile it. Okay, so there are no errors. I rebuild it all again. So right now if you see onto the Nucleo board, the LED is flashing with a 100 millisecond delay, and right now I have given a 1 second delay. So let me program the Nucleo board with this. I'll make the firmware run. So now again if you can see, the LED, the point at my finger is pointing, is blinking with 1 second delay. So this is the third way of generating the code.
In this lecture, we have covered the overview of STM32 Cube, which is an open development environment in which we have highlighted that it contains several software tools, several software packages. Then we focused our discussion on STM32CubeMX, where we highlighted the Nucleo boards, which we have used in demonstrating, and we have used GPIO toggle example, through which we have done MCU pin configuration, clock configuration, and generated the C code. And in the next lecture also, we will be continuing our discussion on STM Cube MX to provide more deeper insight. See you in next lecture.